Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look at a very inexpensive piece of test equipment. Back in the day when you were working on electronics, you might use something like this. This is a logic probe, and what you do is you connect it up to power, you touch the probe tip to the electronics you're testing, say a leg of an IC, and this little device will beep to tell you if the signal is high or low or changing. Well, back in the day when oscilloscopes were very expensive, you would use one of those things as an aid for testing because it's more useful than, say, a multimeter, but still not as good as an oscilloscope, but they were very expensive. Of course, in this day and age, we have stuff like this and this. This one I've reviewed in my right hand here, and these are very inexpensive portable oscilloscopes. This is the more recent one that's going around for about 80 bucks. You've probably seen this on some other channels, and it's a decent piece of test equipment. And I still actually prefer my Hantek there, but that's not the subject of this video. The subject of this video is I want to talk about this little thing here, which is a mini pocket handheld oscilloscope, and I paid a total of $18 for this. In fact, today I went out for lunch and I paid more for my lunch than this thing cost shipped to my doorstep. I know I still have viewers that don't have an oscilloscope, even one of these inexpensive ones that cost $80, and I want to see if something that costs less than lunch is actually good enough to fix a computer. So, without further ado, let's get right to it. So I have my cheap and inexpensive test gear here, starting from left to right. So of course on the left is the Hantek oscilloscope. I made a review of this a while ago. Of course I'll link to any reviews I have for stuff down in the description below. I really like this scope. It has a slightly funky user interface, but this oscilloscope is an actual piece of test equipment that has specs that aren't made up, and it really does work. The design of this is kind of old though. I think this thing came out maybe in 2016, 2017, something like that. And oddly enough, it does charge the internal battery off USB Type-C, so that's a little funny for something as old as this. But because of that, the screen is kind of low resolution, it's a little chunky looking, and the whole thing is really well built, but the user interface is just a little sluggish and a little bit funny. This is the new hotness here, the Zoyi something or other. Lots of channels have reviewed this, as I mentioned. It works pretty well, actually. I think the specs on this are kind of fake and kind of made up, but yeah, it absolutely does work. I did find when I did a little bit of testing on this, and I made a video for my patrons, there are some weird idiosyncrasies on this device that cause some erroneous readings. And for me personally, if you have a piece of test equipment that you can't necessarily trust, that's really not a great thing. I've never been let down by this particular scope. It generally seems to work perfectly. I think it occasionally has crashed on me, like where it just sort of shuts off, but I've never had erroneous readings out of it. But I cannot say the same for the Zoyi. Now, that's not to say a firmware update couldn't fix those issues. And you know, if you watch the videos on this thing, it has a pretty easy to use interface and it does work. I mean, once you just can work around the little strange idiosyncrasies that this thing has. It's also pretty well built, pretty small, and only being $80, it's a really pretty good deal. This scope though, which they still do sell, is down to I think 90 something dollars. So it's come down from the 120 or so that I paid for it originally when I reviewed it. And I'm sure the release of this has caused the price of the Hantek to come down because this is, well, more bang for your buck and still is a bit cheaper, but I'd actually still recommend this scope. It has features that this thing doesn't have, and you know, I like to use this thing. It works quite well. Next is the logic probe, as I mentioned, and these things have been around forever. I think going back to the 70s, it's a simple piece of electronics. You can connect this up to, well, I think all the way up to 12 volts or maybe even more than that. And yeah, it will beep and make flashy lights and things going on, and it's a decent piece of test equipment. But for me personally, I would never use this over an oscilloscope. It might be useful if you're just quickly spot checking something and you're listening for the audio cues that this makes, because of course you have to look at these, and meanwhile with this, you could just listen. But I don't think these are actually that great for troubleshooting. It's better than nothing, but it's certainly not going to be as good as these. And that's because a lot of times I am looking at the oscilloscope to try to find something like a bus conflict or a signal that is not all the way up at 5 volts. It might be only at like 1.5 volts. And that tells me that there's something going on in the motherboard, like there's a bad output driver or there's a short. And these are all things you can't really detect very easily with these simple logic probes. Now these things, I mean, they may have come down in price now, but you know, back in the day, you'd spend $30, $40, $50, $60 for these things. And I think I spent, you know, $20 something for this one which I think is actually a decent brand, Elenco LP560. I don't remember if this is a good brand or not. Look at Sports TTL or CMOS. It's worked pretty well for me in the past. But this thing, like I said, $18 shipped is really inexpensive. Now, I haven't even opened this box. It's got a little warranty seal on it. I did pay for this myself. This is not a sponsored review or anything like that. I bought this off of AliExpress. And I'm really curious to know, like, is this thing even useful in the least? Now, the specs on this, 200 kilohertz, really not very good. What do we really need, though, to work on a Commodore 64? I think that might be fine. 800 volts peak to peak, yeah, ignore that. That just seems like a complete lie. What else do we got here? I don't know, stuff, firmware updates. On the back here, we have some specs, 2.5 megasamples a second, 200 kilohertz bandwidth, 2.8-inch screen, 320 by 240, which incidentally, I have a feeling is the same exact resolution as the screen on that scope. So that's pretty amazing. It does have an internal battery, so this thing does run on battery. Anyhow, nothing much else to see on the box, so let's just pop this open. Let's see what we're dealing with here. Wow, that's really small. Oh, there's our probes. Wow, that's okay, well anyhow, there it is. It's extremely little. A little tilting bail. Looks like USB Type-C. That's the single channel input. Got a little navigation control there. I assume that's a calibration probe or something. These buttons here are clicky, so that's cool. And this is the power button, I guess. And let's just get this off. Really? That failed? I guess I'm just gonna leave whatever screen protector is on here. All right, let's turn this on. Hopefully it's got a charge. There it is. Hey, it boots up really quickly. And it seems like it's updating quickly. A couple things. I don't know or think this thing has any kind of touchscreen on it. So yeah, it's not touchscreen, even though you might think it is with these buttons down here. I think that's just sort of status information. It does indicate that it's got a ×1 or I guess ×10 probe. Let's see if I can figure out how to do anything on here. Let me plug in the probe here. That has a nice firm connection. And I connected the probe up to the outputs on my virtual bench. And let's hit auto. I don't really know how to use this thing yet, so it's like, no, it doesn't even work. It's showing some information there. I think like it's a 5-volt peak-to-peak signal. So that's correct. Why don't we see anything on here? That I couldn't tell you. All right, so this little like button on the top here lets me move this bottom thing around. Does this change? Oh, there we go. Okay, we can do AC coupling, DC coupling, so that's cool. We'll leave it on DC. Aha, the mode button. I don't know what happened there, but I pushed mode and all of a sudden that appeared on there. Okay, so let's see. I want to move that down here so we can see more of the waveform. How do I do that exactly? Obviously, this is time base, so that works as expected. Minimum time base, 10 microseconds. All right, moving this around, I can see here that now that's blue, and that's got to be the trigger point, I guess. And how do I get over here to the waveform? I guess, oh, there we go. So now I should be able to move the waveform down. Hey, this freaking works. $18? I'm already blown away, actually, to be honest, for the price. So let's get this looking a little better. I mean, you saw that it was losing the trigger there. Now, I'm sure the trigger is pretty poor. It's probably a software-based trigger. We'll just set this up in the middle here. But hey, we are actually looking right there at 1 kilohertz, and it's working. Okay, so I just held down the mode button and something happened. It like made the waveform jump. I think it's changing the trigger mode. So it's on a downward slope, and if we push this, now it's on an upward slope. So it's got some kind of triggering going on here. What if I hold the run button down? Oh, hey, that turns off the measurement. All right, that's something. Let's see what else we can do. Can I hold this down? No, that's just gonna change the time base and it just repeats. So we'll just put it back to something sensical. What if I hold this down? That doesn't seem to do anything at all. Now, unplugging the clip leads, I am curious if this has a calibration output right here. It does. Look at that. How did we get the measurements back? There it is, 1 kilohertz. All right, so 3.3 volts. That's obviously what this thing runs at inside. But look at that. It actually has output. It's too bad it's not a normal BNC jack here, so I could use like a regular scope probe instead of being stuck with these silly multimeters. Maybe there's like an adapter you can buy that goes from this to a standard BNC, so then you can use a standard scope probe. One thing that's interesting is it's set to run mode, but it's almost like in normal trigger mode because it's not triggering right now. I guess it only runs in normal trigger mode. It does not run in auto mode. So if we connect this clip lead back up to here again, there it is. The waveform is now visible. And I'm going to connect it up to the output on the bench scope, and there it is, it just appeared. So yeah, it's obviously running in normal trigger mode, and that means for anyone who's a beginner is it will not show anything on screen until it's actually triggering. So make sure you adjust the trigger point there to, like, say in the middle, like it is right there, so that it can actually update the display like it's doing right now. So right off the bat, clearly this thing is a little bit of a toy, but on the other hand, it was $18 shipped. That's it. And this might be actually good enough to try to fix something. So I'm gonna break out a Commodore 64, a broken one, and let's try to do a repair. All right, this is the machine we're gonna be working on today. It says black screen, no line. Well, when I write no line, that means that when you turn on the computer, there's probably no video output at all. So typically you have the video output on the Commodore 64, and if the VIC-2 is working but the system's not booting properly because of, say, some other problem on the computer, you're just gonna have a solid black screen. You have a video signal that's just solid black, but you will often or usually see a white line on the left side of the screen, and that's just normal for a VIC-2 that's powered up. So with this machine, right off the bat, we can tell a few things by these particular symptoms, and we'll need to test again just to make sure that it still has this symptom. It either means that, well, I mean, there's a few things. The VIC-2 could be bad, the power switch could be bad, maybe the whole computer's not turning on, the voltage regulator that generates the 12 volts that the VIC-2 on these older bread bin machines needs, maybe that thing is blown out, maybe it's outputting 18 volts, or maybe it's outputting 0 volts. Also, the clock generation circuit that generates the clock signal for the VIC-2, which then divides it down and generates the CPU clock and stuff like that. If the clock generator is not working at all, that means that the VIC-2 doesn't have a clock signal, and without a clock signal, the VIC-2 is not going to output any kind of video signal. At the bare minimum, the VIC-2 needs to be powered up by that 12 volts or that voltage regulator and 5 volts, and also it needs to have a good clock signal going into it. Now, one of the issues is we're going to need to verify that it has a good clock signal, but the problem is this oscilloscope could do that, but the little $18 one here, which is actually plugged in to charge up there while we're going to look at this Commodore 64, it unfortunately will not have the ability to check for a good clock signal. And that's because the clock signal that goes into the VIC is around 13 or 14 megahertz, or is it 17? I think it's 14 megahertz on the NTSC ones. And that's obviously going to be way too high. But what we can do is use a regular multimeter, and even a very inexpensive one usually can measure clock signals of that frequency. So we at least can kind of try to verify the clock signal with that first, and then we can kind of go on from there and try to see, you know, what's happening on this machine. But with those things I just outlined, we have some ideas of where to start, but I think the very first thing I need to do is take this thing apart, and let's take a visual inspection inside and just see what exactly is going on. I always find it best when doing repairs for machines like this to try to think about like what might be wrong before you even get started. Just think logically about the problems you're seeing. Wow, that screw was in there pretty tight and made a little crack sound. So that means this thing probably has not been opened up either ever or in a very long time. Yeah, same thing with that one. It made a little crack sound and it's very stuck in there. Wow, yeah, really made a loud crack sound. Yeah, as I was saying, I really just like to try to think logically about what might be wrong with the machine before I even start to work on it. It just helps me with that thought process. Look at the top of this machine. Someone drew an X on it. It's got a missing key here. Not the end of the world. I think I have some spare keys. Anything else that looks interesting about this computer? No, not really. It's just really dirty. And it's probably going to make a crack sound when I open it up. Oh, yeah. Okay, so right off the bat, a couple things. This is one of the later bread bins because it's got the cost reduced clock circuitry here with the, what is this, an 8501 or whatever. I never remember the name of this chip. 8701 maybe, or 7501. 8501. I think that's the one. There was a bunch of circuitry that used to be around the VIC-2 and it was simplified down to this one IC. If this chip goes bad, well, it prevents the entire computer from working whatsoever. And it is that clock generator that we're gonna have to start with on the diagnosis. Now, a few observations right off the bat. We're in good shape in regards to the fact that all of the main ICs here are socketed. Absolutely excellent. It makes troubleshooting much easier, especially if you're not good at desoldering IC. So if you're a beginner and you open up your 64 and you see this, well, that's a good thing because you can take chips out pretty easily and you don't have to risk damaging your board desoldering things. I'm going to try to do as much testing as I can with this little device here. And to facilitate that, because these probes are pretty sad, is I'm just going to take the red probe here and I'm going to literally clip it onto this little pick here. And that will allow me to easily probe around on the motherboard. The other clip here, it just needs to, well, this kind of sucks because they are pretty close together here. I'm just going to get another clip lead here. I'm going to clip onto the RF shield here, just scratch that back and forth, make sure it has good contact. And then we will put these together here. And that will just give me a little extra length. I'm just going to push the boots together there so they don't accidentally short on stuff. That will give me a little bit of extra length to probe around the board as necessary with this little oscilloscope. First thing we need to do is we need to check for voltages. Now what we can do is we can use these voltage regulators down here, and we're going to use this thing here because remember, it is showing us the actual voltages because that's the default measurement mode. And actually look at this, how it's not triggering right now, and yet it's running in auto mode. So remember, there's auto triggering, there's normal triggering, which means it only displays a waveform while it's triggering, and then there's stop mode. Well, this thing was definitely earlier running in normal mode, but now it looks like it's running in auto mode. All right, so first thing we're gonna do is I'm gonna move over to there. We're gonna change this to be something more like 5 volts. So when I touch the 12 volt pin here, this actually, should go up to around there, and we should see 12 volts on there. Turn the system on, and let's test right here. That looks like nothing. I'm pretty sure I was on the right pin. Yeah, we're getting nothing there. And on there, we're getting nothing. I don't think we're getting any voltage on this thing at all. So I'm gonna wager the power switch is probably bad here. Let's poke around on the leads right here. Just wanna make sure I don't short anything out. Okay, so that would be the 5 volts right there. Coming from the power supply is ending up on the power switch. And let's see if it's on either of these leads. It's on that lead right now. And then the other half of this is used for the 9 volts AC. So that's not going to be anything right there, but the middle pin right there, no, nothing. All right, so let's look at the power input. In fact, I think it should be on the fuse right here. Oh, aha. It's only on one side of the fuse. I think this fuse is blown. Well, that could indicate a problem. Let's see if we can figure out how to make this thing show us a waveform that looks correct. So that is the AC waveform coming in from the power supply. It's on this side of the fuse right here, but it's not on that side. So we can tell right now that this fuse is blown because it's on the body of the fuse there and it's not on the body on this side. So bad fuse. Now I could of course just try replacing this fuse, but I have a feeling it's just gonna blow again because maybe there's something going on with the bridge rectifier right here, like there's a short in it. Maybe there's a short beyond here. It could be that the regulator itself, and this is the 12 volt regulator here, is shorted. Now this is a 5 volt regulator, this is 12 volts, and these generate the voltages I think that are used on the SID and on the VIC-2, and neither of these are gonna have any power because this is all powered off this circuit here, which includes the fuse. Now with a multimeter, it'd be really easy to check that the fuse is bad, but we really don't need to do that because we know without a doubt that the fuse is blown. And it's hard to tell because of the glare from the lights, but I think that's where the break is, right there. I went ahead and I freed the motherboard from the RF shield and from the case because we're gonna need to get under here to test this bridge rectifier next to see if that's where the short is. So to do that, you're gonna have to take a multimeter and something with a continuity mode. I have my newly replaced EEV block multimeter here, so we don't have any problems with the continuity mode anymore. And let's just flip the motherboard over and you go to where the bridge rectifier is right here. I'm gonna look for any kind of shorts between these pins. Now, if we put the multimeter there, we should not have any shorts between these pins. Nothing is shorted. You might hear a beep normally, but that's okay if you reverse the leads. Yep, everything seems fine. What we were doing is we just want to make sure that there's nothing dead shorted here in the bridge rectifier, because if there is, that's going to obviously create a short immediately. Next thing I'm going to look for is any kind of shorts in these voltage regulators here, and that is not a short. It beeped, but that's fine. You just want to reverse your leads kind of back and forth. just look for dead shorts. But that's not a dead short. Notice I know it's on the edge here, but the resistance was kind of going up there. And we're gonna do the same over here on the 5 volts. Nothing, just some beeping. That's really charging capacitors and stuff like that. So you just wanna reverse your leads, check all the different pins together, and everything seems fine. Okay, next up, before I pop a new fuse in there, is I am gonna remove the VIC2 chip here, and I'm also gonna remove the SID chip. These are the 2 chips that rely on the voltages created by these voltage regulators. So I think at this point, let's pop a new fuse in there. Now I have this other motherboard here that I've stolen a few parts off of to do testing, and I'm gonna do the same thing. I'm just gonna seal this fuse right off of here. Eventually I'll replenish the parts on this motherboard to make a working one, but for now it's just easier for me to steal stuff from it for testing purposes. So there's the fuse. All right, so I have it connected back up to the RF shield, and look at this, if we touch this, we get to see some stuff there. Let's turn this on. Let's see if we see, yep. So the fuse has not blown, and that's good, but we don't have any load on it. But one of these chips could be bad that was causing additional load that caused the fuse to blow. Now the reason why the waveform looks different is because there is now a load put onto the AC input that's coming from the power supply by these 2 voltage regulators. And actually, take a look at this. That waveform looks terrible. This is the 12 volt waveform. Let's look at this one here. That's 5 volts. 5 volts looks completely fine without any issue at all. Now, of course, this is not going to be the most accurate voltage measurement. We should use the multimeter on there. But this 12 volts looks bad. And I have a feeling that's probably because one of these capacitors is no good. Whoa, this one is hot right here. It's mega hot. I think we have a bad cap. That is a first. I mean, it's not a first. I think I've had this once before, but definitely don't usually have bad caps on here. It's a 1000 microfarad at 25 volts. So what's happening with the AC on the 64 is it comes through the power connector, goes through the switch, goes through the fuse, or I don't know, might be going through the fuse first and then the switch. Can't remember which way it is. Then it goes through the bridge rectifier, then it goes through one of these capacitors here, and I think this one here is handling the rectified 9 volts. And yeah, that's still really hot. And then it goes into the voltage regulator, and then out should come a nice clean 12 volts. And I think what you should have here is like 15 volts or something like that. I don't really remember exactly, but clearly when a cap gets super hot, it's not working properly anymore. So I'm just gonna snip the legs of this cap. We're gonna reuse those top legs because I don't have an axial cap here to put in its place. Now I'm gonna use this LCR meter, which is kind of a fancy device for testing capacitors, to test this capacitor. Well, it's showing 423 microfarad, but this is actually a 1000 microfarad cap. But strangely, it shows an ESR of only 0.81. Now it's running at 1 kilohertz there. Let's change this down to 100 hertz, 1.4 ohms, 883 microfarads. I mean, I don't know if that's necessarily bad looking, but clearly there's something wrong with this cap because it shouldn't get super hot. There must be some serious leakage or something else going on with this. So it doesn't even really look bad on here, but clearly this is bad. Okay, I went into my little parts bin. I found this 1000 microfarad, 25 volt Nichicon. And remember, oops, this is exactly what I just took off the board. And clipping this onto the ESR meter here. All right, well, there we go. 0.01 ohms, 955 microfarads and 100 hertz. So yeah, I guess that looks better. The other one, I think, what were we getting a higher reading on here? But not, we weren't getting like 30 ohms or something like that. We were still getting a relatively low reading. So who knows? Anyways, this cap should be fine. Problem is, this was pulled off of some other board, so it has super short lead. So I'm gonna have to kind of bodge that onto there. All right, so there we go. The random capacitor is connected up, and I just used this off-cut of wire. It's all pretty ugly, and it's sort of flopping around in the breeze, but ultimately, don't be afraid to use spare parts you have lying around just like this. And all I need to do to kind of secure this is just use a little bit of hot glue on the motherboard to connect this capacitor down so it doesn't just flop around. And even though this is super ugly, this should absolutely work properly. So let's take a look now at the 12 volt output on this when we power this thing on. First of all, is this cap getting hot? No, it is not. So now when we look there, take a look at that. We are seeing a really good, clean 12 volt output now. And it looks like it's running a little bit high. 12.6. Let's take a look at it with the multimeter. I don't really trust this thing to be very accurate when it comes to measuring voltages. And I'd say it's good to make sure the voltage you're about to put into your VIC-2 chip is actually pretty good. Ah, that is a bit high there. Look at that. 12.8. I don't trust that. I think that's high because it probably was potentially getting damaged by the excessive ripple that was coming through that bad capacitor I removed. And it's the next day. I had to take a little bit of a break. Let's get back to testing this little mini scope and see if I can get this Commodore 64 working. After I stopped recording yesterday, what I ended up doing is I ended up swapping out the bad 6812 voltage regulator. So here is the bad one that came from the motherboard. There's the bad fuse, there's the bad capacitor we found. I also used this eraser pencil thing that a viewer sent in, and I cleaned up the contacts here on the user and cassette port. You may have noticed, I didn't really point it out, but these were looking pretty crusty. And well, this little thing made really quick work of it. I think any kind of pencil eraser would work well, but this one is just extra convenient because it's in a little pencil shape. You may be noticing as well, the motherboard looks a little bit cleaner, and that's because I gave it a quick wash. It was so dirty. Everything that was touching it, including like the mini scope here, sitting on top of the RF modulator, was just getting filthy. So yeah, I gave it a clean, and it's had all night to dry. I added a little bit of hot glue as well to hold down my little horror of a capacitor replacement. And I just want to mention again that yes, I could have used a proper axial cap to do the replacement. I don't keep any in stock. Or even I could have used a new radial cap with longer lead so it wouldn't have had this whole wire. But I really just wanted to show that you can use stuff you have lying around to fix stuff. And yeah, it doesn't look perfect, but this computer, when it's done, is going to be back together in its case, and no one's ever going to see that it has that kind of ugly mod. And if anyone ever put this in a clear case and wanted it to look perfect, well, you can just go ahead and replace that capacitor and that wire. I'm approaching this particular repair as something that you can do very inexpensively, which is why I'm going to try to use this $18 scope as much as possible. All right, enough talking. Let's get back to troubleshooting. All right, let's turn this thing back on. Now, what I haven't done, there we go, it's booted up. What I haven't done is tested out the voltage here that's coming out of this regulator post replacement. Look at that. That looks perfect. No more ripple, but also, well, of course, no more ripple because we fixed the capacitor problem, but also notice we don't have that high voltage anymore. It's obviously just slightly below 12 volts now, which is perfect. Let's just double check the output of the 5-volt rail, and I'm gonna say that that looks good as well. I just changed this over to 1 volt per division, so when we touch the 5 volts here, we're going to have more resolution, so to speak. The more appropriately set the per division voltage rating is means that it's going to have a bit more accuracy on the measurements here. And now you can see that we're actually much closer to 5 volts. In fact, we're pretty much just exactly at 5 volts now, which is basically perfect. Okay, so the power side of this machine is completely working perfectly now. It's time to put this VIC-2 back in here, and let's hope that it didn't get damaged. I mean, the 13 volts this was outputting was fine, but that ripple wasn't a good thing either. So hopefully this thing is fine. It probably is going to be fine. I'm just going to give these chips a little bit of a push here. There we go. Okay. I'm going to leave the SID out. We don't need the SID for operation of this machine. A few things I've noticed, by the way, there are some MOS ICs here, so those are problematic. The RAM is Fujitsu though, which is generally reliable. It's not like MT RAM, nothing specifically bad about it. And of course, finally, the MOS PLA that's in here is very suspicious. These things, well, you can always suspect they're bad, and it's very nice that it's in a socket. For the next phase of this repair, I need to look at the schematics, but one of the issues is my setup here. I don't really, well, I'm not set up for using these types of things where I'm not looking at the oscilloscope on the desktop of my computer, which means it's kind of hard for you to see what I'm doing and to see the output of the scope. So I think I'm going to just try to position this close to what I'm testing and hope the glare is not too bad, and yeah, like that. All right, so the first thing we want to look at when we turn this computer on is we want to see if there looks to be a good video signal. That's a really good way to know if your monitor or your capture device is working correctly. Because occasionally, like, you plug in something like RetroTink or some other scan converter, and it may not be working, or maybe whatever monitor you're using doesn't like the Commodore 64's video signal. So using a scope like this, even something cheap like this, we should be able to see a video signal. And that is on pin 15 right here of the VIC-2. This thing is outputting some kind of video signal. So I'm going to use this little pointing device here. So that is the white line on the left side of the picture. So this is one scan line, and this is the horizontal sync pulse. So right here is where the beam on the CRT goes back to the left side. and then it scans across the screen. And if we had content there, for instance, blue borders or text, you would see stuff in there. And we're not. We are just seeing always the same thing here, which is absolutely without a doubt a black screen. This is pretty cool. There are a lot of limitations on this particular device, but it is still good enough for us to see that there's a video signal, and we've confirmed without plugging this machine into anything that we absolutely do have a black screen. This is something you could not do with a multimeter or with a logic probe. Now zooming into the VIC2 here, this right here, pin 17 is phi out or phi 0 out. That is the clock signal that goes to the CPU. Should be around 1 megahertz. It's pin 17. Let's take a look at what that looks like. I don't think we're gonna be able to see anything with this device, but we should see something. All right, well, I mean, that's something right there. So going down to 10 microseconds per division, that is the lowest we can go to. And you know, unfortunately, I think what we're really looking at there is just aliasing. This thing is just not fast enough to show us a 1 megahertz frequency. Now we knew that, of course, this thing's only rated for 200 kilohertz. It does show us that there's a signal though. If this were stuck at 0 or 5 volts, then we know that there's something wrong and there's no way the CPU is gonna run. But that is showing us something is there. Now, just for fun, let's just poke around on some of the other pins on the VIC2 here. So starting on pin 1 right here, I mean, we have something going on there. Now, pin 1 looks like data line 6, which, you know, I have to say looks very suspiciously bad, actually. That does not look correct. Pin 2 is data line 5. I mean, that looks like more like a data line, what I would expect it to look like. Remember, at 1 volt per division, so 5 volts should be up there. That is pin 3, data line 4. And I'm on pin 7 here, which is data line 0. And again, that looks a little weird. I'm just gonna power cycle the computer here. Use my left hand to do it. Yeah, now it looks fine, look at that. So it was weird looking, and then now it looks the same as the rest. Let's check out that pin 1 again. Now, the problem is here is there could be some activity that's just happening more quickly than this scope can resolve. And we're just looking at some aliasing there. So that might not really be a problem, actually. It's hard to know. Having not used this thing on a real working machine, it's not gonna be easy to tell. Now, where this thing should be useful is on the output of the PLA here, which incidentally is quite warm. I have it up on my screen. I know you can't see what I'm looking at, but I'm going to be looking at the output lines. These are the chip select lines that come from the PLA that go to various things on the computer. All right, so let's start on pin 10 on the PLA here. This is ROM H, I think, ROM high for the cartridge slot. So that's fine as long as it's not stuck low. Then we go on to pin 11, ROM low, same thing, looks totally fine. Pin 12, this is the IO line, and let's power cycle the computer here. Oh, I was touching the metal thing here. Look what happens. It picks up the lights around me, so make sure I don't do that. That looks fine as well. It's not stuck low. Pin 13 is the GRW line. I think this goes to the color RAM, so that's fine. It's not selected right now. Next up is the character ROM selection, and we can see little spikes happening there, but it doesn't look like it's stuck low, and that's what I'm really worried about. Now, no characters are being drawn to screen, so really there shouldn't be anything selecting that ROM at this time. The next one is the kernel ROM, pin 16. It's not really being selected either. Then we have the basic ROM, same thing, not being selected at all. And then we have the CAS RAM line. Now, unfortunately, I think this line is running at a speed beyond the capabilities of this little oscilloscope. This is where we're gonna run into limitations of this thing. It's just not gonna be able to resolve that signal. It can't go any faster than that. And this is exactly what I'm talking about. I'm on the same pin, but I'm using this little Zoyi now, and it says it's running at 2 megahertz. This is the same CAS RAM line. Yeah, and there's just no way this can be resolved on that other little scope. Now, this signal looks fine. It's not triggering properly, but that's fine. It's just the trigger point is in the wrong spot. There we go. Now it's in the right spot. And yeah, I mean, that's the difference between something that actually is able to resolve multiples of megahertz versus something that's not. All the other lines, though, that we've already looked at, they look fine on this scope, just like they did on the other one. Now, the funny thing is, because we're not seeing any kind of weird problems with the PLA on this machine, actually looks like it's operating normally. Let's go look at these data lines again, the ones that looked funny on the other one. Aha. So this looks like normal activity, actually. What looked problematic activity on the other one looks fine on here. Now, if we zoom out a little bit, yeah, there we go. So we have kind of normal activity on the data line. Now, all this extra overshoot, just because I'm using this screwdriver as a probe, is actually okay. So looking at each of these lines, it looks okay. Taking a look at the clock signal, which we couldn't really resolve on the other one, there it is, 1.02 megahertz, so we know that is perfect. And this is the video signal, which we were looking at on the other one. If we zoom out here, we get much clearer view of the video signal, the sync pulses, and then we have the white line. And there's definitely nothing on screen. This computer is for sure not running. Now, one thing about this machine is it has been turned on now for several minutes, and what I want to do is I'm first going to look for any chips that are super duper hot. The CPU is very, very hot. That's a suspect chip right there. It's much hotter than I feel that should be. PLA is warm, but nothing extraordinarily hot. VIC2 is very hot, but that's par for the course. Let's check out these ICs here. So feel around for the RAM chips. You don't need to use a thermal camera for this. You just need to use your senses. So far so good, nothing is burning hot. A bad RAM chip can often manifest itself as like a burning hot chip. So you have like one that's bad. Yeah, this stuff all feels fine. Now, I'm used to 64s. If you're fixing one for the first time, you're not going to know what's hot and what's not. SID chips get hot, VIC2s get very hot, PLAs get pretty warm, ROM chips get warm-ish, the 6526s kind of warm. CPU though, it's super hot right in the middle where the die is. I think what I want to do next is let's take a look at the address lines. We need to make sure that this is addressing the ROMs correctly, because the system is not going to boot at all if the CPU or say one of the address lines, maybe due to some other chip to be honest, has an issue. So let's look at the address bus. We look at the data bus already, and we looked at it on this, which wasn't super conclusive. We looked at it on the other Zoyi, and that was definitely more conclusive. But address lines are definitely the next thing we need to look at. When the 6502 or 6510 in this case initializes, it tries to jump to a reset vector, which is like FFF, A, B. It's right at the top of memory space. So the very first thing this thing should do is set up the address bus as such that it's going to start booting from the kernel ROM. The PLA maps the kernel ROM into that address space, that top of the memory, and that's what the CPU needs to do when we turn it on. We're going to start on pin 7 on the CPU, which is address line 0. I'm going to turn on the machine here. Okay, it has lots of activity, not necessarily a bad thing. And I'm just going to go down the line here and look at all of the address lines. Just looking for anything that's like kind of out of the ordinary. You know, we see normal activity going on here, which is okay. Goes all the way up, by the way, to pin 23. So I'm looking for anything that's like, 2 volts, or say it's just stuck at 0 volts all the time. I mean, being stuck at 5 volts like that, not the end of the world. It's just power cycling the computer there. Oops. So there's some activity. We're not able to really resolve it because this thing just has limitations, obviously. 19, pin 20. Wow, those are just stuck. I don't believe those. Those look wrong to me. See how this is just really held hard up against 5 volts, but this address line has activity, and when I turn it off and back on, we see some differences there, but these two lines, look at this. That's like a dead short. So pin 22, which is address line 14, it looks like a dead short. And the same thing goes for this next one here, pin 23, address line 15, absolute dead short. All right, so there's a couple things we can do. We can pop the CPU out. With the CPU removed from the system, those pins should not be a dead short anymore. They should be just kind of floating. So let's turn this back on here and let's take a look. Okay, looks like a dead short still. And same with that one. Let's power this thing off and on. Yep, that does not seem right. Let's go over to one of these pins that was not like that. And there is activity on them. So when talking about address lines on the C64, the higher address lines, which are the ones that look like they're dead shorted, they don't go to that many things. They don't go to the ROM sockets, for instance. So it's not the ROM that's doing that. Oh, and you know what? Take a look at this. They're actually pulled right up to 5 volts through a resistor pack. And I'm pretty sure it was actually these 4 lines that we saw that were held up there at 5 volts. Okay. So that means that dead short that it looked like was by design because it has those 4 lines pulled up. Now, my problem is if this CPU were working, even if there was like a dead chip, like the kernel ROM were bad, I have a feeling we would see more activity on those lines than we are now. We're just seeing absolutely nothing happening at all. And if you're asking the question, why are we seeing activity on the address lines with the CPU removed? That is because the VIC-2, if it's working, is sitting there trying to refresh its screen, and it's trying to read from screen memory to do that. And to do that, that means the VIC-2 is actually accessing the DRAM and the color RAM on the machine, even without the CPU in here. And if I recall correctly, the AEC line, which is the output on the VIC-2, is what tells the CPU, hey, release the address lines and let me drive the address bus. And it comes into the CPU right here on pin 5. We should take a look at pin 5, even with the CPU removed. And we just need to see that line, I think, should be toggling. And indeed, right there, we see there is activity on it, although it's, we can't really see it clearly. I'm pretty sure what happens is when this line is asserted, the CPU goes into a halt mode and disconnects itself from the address bus and the data bus, actually, for that matter, and then it sits there and it waits. If this line here on the scope were just stuck low or high all the time, that would be a problem, actually. But the fact is there's some type of signal on here that is not low, which definitely indicates that I think the CPU should be able to execute in between these pulses. So I have my parts board, the one that I stole the fuse off of. I'm just gonna steal the CPU off this now. I don't actually know if the CPU is working on here, but we'll just have to make an assumption that it is. And just so I don't mix these up, the one I just took out of the parts board has a yellow dot on it already, something that I didn't do. And this is the one in my right hand is the potentially bad one. So we'll just pop this in here. The machine is turned off right now. And one way to know the system is actually executing any code is to look at the chip select line that goes to the kernel ROM from the PLA. It's pin 16 on there. And let's turn this on now and see if we have any activity. Oh, we do indeed. So that is something we did not have before with that other CPU installed. That implies that this system right now is actually trying to execute. Now this CPU isn't even warm at all. Why don't we take a look at the video signal on this little scope here. Whoops, that is pin 15 here. 15, there it is. Okay, well, we can tell right off the bat at the video signal that we have a border. I don't know if we have anything on screen, any text. Oh yeah, there was. Did you see that? Oh, this thing is working. Whoops, I fell off the pin. So what we're looking at here is the video signal. I'm just trying to make it so it's not glary here. And you see how occasionally there's stuff there? That is freaking text on screen. So that is the border, the lighter border, and then the darker background. And then the bumps we see there is the text. So without a doubt, I don't know if this thing's working perfectly, but it is not a black screen anymore, and it is showing text on screen now, and we have borders and stuff like that. We have a big improvement. If I power cycle it, you'll see the black screen for a little while with the white line, and then it will display the border. Watch. There it is. Boom, there it is. There's the border. So right there, this thing's good enough for us to tell that we have a good video signal. Let's hook up the capture device. Okay, there's the RetroTink. I have it set for composite. Let's power this on. Let's see what happens. Come on. Ah, look at that. It freaking works. I knew it. We could tell that it was outputting text because we could see it on the mini scope here. And it's working. It's freaking working. How awesome is that? All right, SID chip is in there. Let's get something hooked up to the audio here so we can hear the glorious SID sounds. Let's put in the diagnostic cartridge first. We should actually try that, right? So here's the diagnostic cartridge. Let's see this, if this works. Could be still a problem with the PLA. Oh no, look, it's actually running. Now, unfortunately, I don't have my test harness for connecting to this thing for final testing, and that's because I lent it to someone who needed to test several machines. So for now, we're just gonna have to use diagnostic ROM without the harness, which will give a bunch of errors here, but we should be able to hear the SID working. And then we'll try out the good old, you know what? I won't say the words, but I think everyone's thinking it. Ah, there it is. So SID is working. Cool. While the diagnostic is running, what I wanted to do is probe around on a couple data lines and address lines and things like that so we can kind of see how it looks on this thing while the system is operating normally. So I'm on the kernel ROM on pin 9, which is data line 0. And while we can't get a good view of what's actually happening on this line, we do know that it's not stuck at 5 volts or stuck at ground. It looks, I'm gonna call this normal, It'd be nice if this had higher resolution so we could resolve more stuff than we're seeing there. It looks almost like noise. But that's what happens when you look at a signal that's too fast for an oscilloscope on something that's running too slowly. And here we are on address line 0, and also that just looks kind of like noise because there's a ton of activity on that particular line and it's just not able to resolve it. And here we are on a higher address line, and again, we just really can't get a good view to see if this is bad or good. But what I can see, even though I can't clearly look at the line, you can see that it's being driven correctly up to 5 volts, well, or a high signal, which is like 4 volts-ish in this case, or all the way down to ground. And that tells us that this particular address line is actually fine. There's nothing wrong with it. And moving on to the next one, same thing. So you can see that there's bursts that go down to 0 and then bursts that go up high. There's a lot of stuff in the middle there, which, I don't know. We can't really tell what's happening on this thing, but it's giving us an idea that that line is actually good. Incidentally, I looked in the manual, and by the way, it goes over the short and the long pushes on this particular thing. It tells you all the various differences. There's some kind of automatic calibration junk, I didn't even bother with that stuff. But it looks like here it does say auto, single, or normal switch settings. So you can do single shot mode by pushing a short press there. That's kind of cool. And then we already figured out here the rising or falling edge for the triggering. And then it's the run button, the short press, which will run or pause the waveform. And then we figured out that long pushing it will open and close the measurements. And this thing does support a 10x probe. You're going to need to use some kind of adapter because clearly you're not plugging a normal 10x probe into this little funny little jack on here. I looked online, I did see them selling adapters, but when you get the adapter plus a probe, it ends up adding another $8 or $10 to the price of this thing. And then you're at like $30, and I'm not quite sure it's worth it at that point. For the very rudimentary stuff we're doing here, frankly, using the clip leads and that little pointy thing is, well, it's been good enough, right? All right, so let's pop in the Easy Flash here. This thing is a tricky cartridge to run, so if it doesn't work, then there's obviously more things wrong with this computer. So let's power on the machine. Hey, look at that, it did come up, and good. I can go to Adrian's tools. That was my fault there, Adrian's tools. And let's run the 8-bit dance party. I have the sound turned down. Okay, well, anyhow, that sounded perfectly good. I'm going to say that this machine is fully fixed. I won't know 100% for sure until I can use the test harness on it, but obviously we have good SID sound. The CPU is running now. It's working well. All right, so there we go. The question of can I fix a Commodore 64 with this mini oscilloscope? I'm going to say resoundingly yes. Is it ideal? No, not really. Would I recommend you get one of these? Well, if you don't have any oscilloscope at all, and you don't really even want to spend like $80 on something like this, or even I think it was like $57 for the cheaper 1-channel version, which also has a smaller screen and lower bandwidth, well then, yeah, I mean, this is absolutely 100% without a doubt better than having no oscilloscope at all, because as you saw, we were able to validate that the power rails look good, we were able to find that bad capacitor, we were able to see that the video signal was good on this thing and we were getting a black screen. And then we were also able to validate those upper address lines were stuck at 5 volts, which really implied that the CPU was not trying to drive them. And of course, the CPU being burning hot was also as kind of a smoking gun for a problem with that chip. And then once I swapped out that chip, I was able to see on this, before we even plugged this into any video device, that we had a working video signal with the borders and text and everything. And that is all something you just cannot do with a regular multimeter or a logic probe. So for 18 bucks, if you have nothing and you don't really even want to spend the money on something like this because you're just such a casual user, then yeah, this thing's pretty good. Now, I think it was on sale when I got it for $18. If this were, say, $35, I would have a harder time justifying it. I know the increase from $35, if that's the regular price of this, for instance, all the way up to $56 for the cheaper version of this, is not nothing. It's not like that's no money. But the thing is, this truly is a decent piece of test equipment. It's not great, I don't love this by any means, but as you saw when we did a comparison, we were able to resolve signals very clearly on this when this thing was just unable to resolve those. We could tell there was a signal there, it just wasn't showing us any detail. It wasn't able to count the frequency or anything like that. Not to mention, this Zoyi thing is actually a multimeter as well. It's not a good one, but it is one. So if you don't even have a multimeter, then you're gonna getting 2 for 1 with this. So yeah, the 1-channel version of this, probably better than this, but again, $18, less than I paid for my lunch yesterday. This thing does work. It really does what it says it can do. I don't feel the specs that this thing says it is, 200 kilohertz, is even a lie. It seems truthful to me. And in all honesty, it's quite amazing we live in a time where you can go out and buy something so cheap that's actually seemingly well built, like this doesn't feel cheap and crappy, and yet it does freaking work. And I was able to fix this Commodore 64 with this. Of course, a bunch of knowledge that I have on fixing them, but nonetheless, I feel that I was able to see stuff with this, and I hope I showed that in this video, that really did aid me in fixing this. And I would have had a lot harder time fixing this board if all I was armed with was a multimeter and a logic probe, or even just a multimeter. Yeah, this absolutely did help in the case of fixing this. And really, I cannot recommend enough, if you're working on repairing anything and you want to go beyond just parts swapping, like parts cannon, chip swapping, recapping, that kind of stuff, having an oscilloscope is an absolute essential tool. So anyways, I think that's going to be it. I'll put a link to this thing down in the description below. Like I said, I paid for this, and I don't get anything out of you buying them. There are lots of other reviews of this Zoyi one out there, so just type in Zoyi oscilloscope if you're trying to find a review of that. I really want to thank my patrons for all the support I get here and the channel. It makes it possible that I do this full time. Their names are shown up the side of the screen over here. If you want to become a patron, you can do so. There's a link in the description below, all that stuff like that. They get behind the scenes things and whatever, all sorts of good stuff like that. And I think that's going to be that. If you enjoyed this video, I'd really appreciate a thumbs up. Check out my other videos, second channel, all that good stuff. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.